Welcome back to the HiSeq Expert video tips series. In this video, we will continue providing tips for the HiSeq Fluidic system, something we began in part 4 of this series. Also, if you've not already done so, be sure to check out parts 1, 2, and 3 of this video series. Part 1 provided tips related to sequencing primers. Part 2 discussed tips for the instrument computer. Part 3 covered best practices for the thermal system, mechanical system, and instrument maintenance. A useful skill to have when operating a HiSeq is how to determine where a fluidic line clog or blockage is located. Clogs can be identified by two characteristics: slow flow or no flow at all through the flow cell lane, or backflow as seen here. Backflow can result due to the binary splitting of reagent lines. Lanes 1 and 2, 3 and 4, 5 and 6, and 7 and 8 share a direct connection just before where the reagent enters the flow cell. A blockage in one of the lane pairs can cause the pull of liquid in reverse towards the inlet port through binary split and back through the flow cell through the partner lane. In this diagram, lane 5 shows backflow, while lane 6, its pair, shows faster than normal forward flow. To determine the location of the blockage, we investigate 3 general zones of the fluidics path. The first is from the reagent bottles to the inlet of the flow cell. The second zone is the gaskets and actual flow cell lanes. And the third zone is from the back or outlet of the flow cell to the syringes and out to waste. A good way to determine the location of your clog is to eliminate each of the 3 zones one by one as being a possible source. If the clog is occurring somewhere between the reagent bottle and the front of the flow cell, then all lanes are affected. This is because there is a single sipper aspirating reagent from the reagent bottle into the fluidics line, and that eventually gets split into 2, then 4, then 8 lanes just before entering the flow cell. A clog in this fluidics zone could occur before the binary splitter or during the splitting. First, verify that there is sufficient liquid in the reagent bottle you're pulling from and that the sipper is in the bottle. Next, change the reagent bottle position in the flow check settings. If the issue is specific to line from reagent position 5, for example, then reagent position 6 would not be affected. If the clog is not specific to one reagent position, then the blockage could be in an internal valve or due to improper front or rear manifold movement. Please contact Illumina Technical Support to schedule a service visit for your instrument. If a single lane is blocked or there is slow flow, then the issue may be with the gaskets. As we demonstrated in part 3 of this video series, flipping the orientation of the gasket in the front or back of the flow cell can help determine if the blockage is related to the gasket. If the blockage follows a particular inlet or outlet on the gasket, replace gaskets with new ones. If the blockage remains with the original lane or lanes, then the gaskets are not the source of poor flow. The inlet and outlet ports of the flow cell may not be aligned with the gaskets. Visually inspect the alignment and position the flow cells to ensure proper flow. If the clog is in a single lane and there is backflow associated with it, then it is likely that the blockage is from the back of the flow cell to the syringe pumps. Monitor the syringe associated with the block while pumping and check for large air gaps. If air gaps are seen, perform an instrument wash to push the air to waste gradually. Ensure that the solenoid valves atop the syringe pumps are functioning properly, but switch positions. The solenoid should click and change LED indicators when working properly. Let's go to Tim for some tips on clearing blockages.
Thanks, Chad. Now that we know where the blockage is located in the fluidics line, we can try clearing it out. If the clog is from the outlet of the flow cell to the syringe pumps, you can clear clogs or large air gaps by performing a flow check and manually loading warm water into the outlets. We recommend heating 100 milliliters of water until it is warm, approximately 40 to 45 degrees Celsius. The warm water can help dissolve any salt deposits or solid blockages in the lines. To do this, remove the flow cell and gaskets and pipette the warm water into the outlet manifold well. The outlet manifold can only hold about 100 microliters in the shallow well, so be sure to add warm water continuously as it is drained. This process allows you to run water quickly through the back portion of the fluidics without introducing variables such as the flow cell or gaskets.
This concludes the HiSeq Expert Video Tips series. Over the course of the 5-part series, we have covered numerous tips, troubleshooting advice, and best practices for running your HiSeq instrument.
We hope by showing common tasks related to the computer, fluidics, thermal, and mechanical systems, as well as maintenance best practices, we have enabled you to drive your research forward by utilizing the HiSeq to its optimal capacity. Remember that there is a wealth of HiSeq resources on www.illumina.com, including instrument user guides, reagent kit reference guides, and online training tutorials.
Finally, keep in mind you have an entire support team to lean on, from your field service engineer, your field application scientist, your territory account manager, to technical support and customer service. We all work as a team to help you get the most out of your HiSeq instrument, and we're happy to help.
And as always, thanks for being part of the Illumina community.